Okay, so this video is to review you for mainly for linear regression. We're also going to talk about exponential and power law regression just a little bit, but the main thing is the concept of linear regression and what you need to know in that regard. So that's one. This is from chapter 3 in your book, and certainly it's one of the main topics of AP Stats. We'll see how much of it's on this year's test, but anyway, so let's look at a couple of contexts here and see what we need to do. So this one says a university hosted 9 football games this year. The athletic director wishes to see the relationship between the number of ushers working at the stadium for a game and the number of complaints that were received after the game at the stadium service center. And says draw a scatter plot of this data and describe the relationship. So you notice, first of all, this is quantitative data. It's not categorical. You can't do regression analysis with categorical data, so to speak. Anyway, so and you notice the data is paired. Okay, that number goes with that one. That one goes with that one. That one goes with that one. Okay, this is the number of ushers that were there that game. That's the number of complaints. So in other words, if you were to change the order of the numbers like on one of the lists, it would totally mess everything up. So we want to see the relationship between the number of ushers and the number of the complaints, and so we draw a scatter plot, and when we comment on the scatter plot or we describe the relationship, that's DOFs. That is direction, outliers, form, and strength. And so all you have to do is just draw a little, just graph each of these points, 42 and 80 and 46 and 84, and draw a rough sketch of all of those points all the way to 90, 58, 90, 58 to be there. Make sure to label and scale your axes, and then DOFs, direction, outliers, form, and strength. So you'd say there's a negative, and negative means in general it's going down from left to right. All right, it's linear, means there's no noticeable curve, and moderately strong. Now the R value is going to help us with that, and we're going to talk about that in a second. But I would call that moderately strong relationship between the number of ushers and the number of complaints. Make sure and include the context, and there appears to be no outliers. Now, in general, if there's not any outliers, you really don't need to say that, but it'd probably be a good thing to say. So yeah, so that's how you would describe the relationship. And outliers are points that are way above or way below the pattern of the other points. All right, so that's the first basic thing. And that could vary. I would not be surprised at all if that was on the exam this year, where they give you a scatter plot and ask you to describe it. And you have to talk about, whether it's a positive or negative, is it linear, or does it show a noticeable curve? And how strong is the relationship, and is there outliers? So that you need to make sure and be cool with that. So then the next thing says find the equation of the least squared regression line and evaluate its effectiveness in describing the pattern. Now, I hesitate to do this because doing what I'm fixing to do with the calculator is probably not going to be on the exam. What is going to be in the exam is what we're going to talk about in a second, or if they do a regression thing, and that is a computer printout. All right, you have to know how to read the computer printout. Nevertheless, there are some points that I wanted to make in that regard, so I am going to use the calculator to do this right quick, although I'm not really going to emphasize this. So what we would do to find the least squared regression line is to enter these numbers in our calculator. So we would go stat, we hit the stat button, and then go edit, and in list 1 I put the number of ushers, list 2 I put the number of complaints, like that. And this is how you create the equation line to find the R value. So you hit the stat button right there, you get stat, and then you go calculate and go down to the number 8, linear regression A plus BX. You would enter list 1 there, list 2 there. Of course, if it doesn't say anything, you do like hit second, hit the 2 button to put list 2 there. Frequency list, leave it blank, and store regression equation in Y1. And to do that, there's a couple different ways you can do it. You could hit the vars button and then Y vars, enter, like that, or you could go to F4. But anyway, and so we go calculate, and so there is the equation of my least squared regression line, and there is my R value. So anyway, and so there's the equation. Make sure to define your variables. There's your R value. Now the residual plot. What the residual plot is this. It is a plot of the vertical distances between the line and the point. And I'm going to show you how to do that in a second. But the main way when it says evaluate the effectiveness of the line is to look at the scatter plot. We need a nice linear strong relationship. We need a strong R value, and we need a randomly scattered residual plot. So I think what is plausible, they're probably not going to have you graph a residual plot on this test, but they could have you comment on one. And to comment on one, you would look and you'd say, is it randomly scattered? Which this one's pretty randomly scattered. But if it shows a noticeably curved pattern like a parabola or something, then you would say that this is not a good model equation. But so to draw the residual plot, after doing this regression command, we can do a scatter plot of list 1 and the residuals, because this will automatically create the residuals for me, this command. So if I go second stat plot and then hit enter, and then the scatter turn on, and then there's the scatter plots, the first graph, list 1 and residuals. The way you access the residual list, by the way, is going second list, which is above the stat button. If you go second list and scroll down to residual, and it puts residuals there. And then before I hit the graph button there, what I'm going to do is hit my y is equal to, just to turn that graph off by hitting enter on the equal sign. And then I can just hit graph and then go zoom 9, and then there's my residual plot. Now, once again, I hesitate to do all that calculator work because that's not going to be in the exam, but what could be on the exam is they give you a model equation and they ask you to comment on, is it an effective model? And for this one, this is what I said. I said I feel good about this equation being this equation. I feel good about using that as a predictor, all right, because of the linear scatter plot, the marginally strong R value, and the randomly scattered residual plot. So, and this one is a bit of a borderline case because that's, negative 0.748 is kind of borderline. That's kind of marginally strong. So, anyway, and so that's how you do that. All right, and so then we have this. All right, so it says in number 1, another game is added to the data. For this game, there were 10 ushers and 96 complaints. What do we call this point? What happens to the R value? So if we look at this graph, all right, so we've got our equation. So if we were to graph that line's going to go right nicely through there like that. So 10 is off of this scale. There's 40. So 10, so the point 1096, the point 1096 is up here. It's really close to the line. Now, that's what we call an influential point. It differs a lot in the x direction. And because it's close to the line that is the pattern of the other points, it's going to make R shoot up really high. And so what we would say there is this. That is an influential point because it differs a lot in the x direction. And it makes the R value, if we were to find the R value now, it makes it go up to negative 0.86, which is much stronger. So this one point can make it look like our model is a lot better. So we need to be really wary whenever we encounter an influential point. And then it says this in regards to number 4. It says in number 3, instead of 96 complaints when there were 10 ushers, there was actually 44. So in other words, as opposed to here, we add another point there's like way down here like that. And so what's going to happen there? So as it turns out, now if you just add that one point, and you can try this out with your calculator, it makes the R value go down to 0.0965. Okay, 0.0965. And what happens to the line? The line is going to get pulled down by this one point to where it makes it like not a useful thing at all. And so you always need to graph your data and look for a point like that because it can mess up the line for the other points. And so right here without the point, we've got a line that we feel pretty good about predicting. But now with this one point, because it differs so much in the x direction, gives it a lot of power, kind of like a long lever in science. Right, it's going to pull that line all the way down to it and sort of messing it up. And so, so ask the question, what happens to the slope if you were to add that line? Well, it changes greatly. Now it's much flatter. It's much flatter. So anyway, it's actually even positive now. So anyway, so that is that. I just wanted to do that to show you the influence of an influential point that differs a lot in the x direction. Okay, now. Please don't be too distracted by the calculator work. Here's kind of the main thing you need to be able to read and the main thing you need to be able to do, and that is with the computer printout. So this context this context says this. It says, a worker for a car company wishes to see the relationship between the average speed in miles per hour that a particular type of car has while being driven for 100 miles and the gas mileage that it gets for the 100 miles. And so the regression data for the study shown below. And so here is our computer printout which you have to be able to read. So they're describing the relationship between how fast the car was driven and the gas mileage it got in miles per gallon. Now, this computer printout, this is what you got to be able to do. This first number is A. That number is A, and that is your y-intercept. And the second number is B, the one that's right below it. These numbers up here you will never use. These numbers here we would use in Chapter 12, but we're not doing Chapter 12 this year, and it's not going to be in the exam, so we can X those out. All right, and so, but this is an important number. That's the standard error about the line. We'll talk about that. There's r squared. That's a very important number. We'll never use r squared adjusted. So it's these four numbers you got to be able to understand. You have to be able to describe in context. That very much could be in the exam this year, big time. And so anyway, what's the equation of the least squared regression line? Well, always put a hat on your y, and so it's y hat is equal to that, and then there's the slope like that. And so always define your variables. X is the speed in miles per hour, and then y is the gas mileage in miles per gallon. So that's how you look at that and get the equation of the line. Then to interpret these things in context. These are very asked about things. To interpret A, B, S, R, and R squared in context. So the first of all is A. What is it? It is the y-intercept. Okay? And what is a y-intercept? The y-intercept is what we predict y is going to be when x is 0. But we can't use x and y. We've got to say the variables. So it says if a car speed averages 0 miles per hour, we predict that it will get 61.08 miles per gallon, which in this case doesn't make sense in this context. And that happens a pretty decent amount with the y-intercepts. But so in this case, that doesn't really make sense in this context. But the slope should always make sense. All right? So the slope is that number there. And so what the slope is to us is for each increase in speed in 1 mile per hour, we predict the gas mileage will go up by 0.723 miles per gallon. So yeah, the slope is what we predict is going to happen to y when x goes up by 1. And so you have to say it in context. That is the most asked about thing in all of linear regression. So please be able to do that. Then S. S is that number there. It is, in essence, the standard deviation of the residuals, the average of the residuals. It is it is the average amount our predicted y values would be off. And so the way you'd interpret that in context is you would say predicted gas mileages, predicted y values, using this model will be off by 2.20 miles per gallon on average. So when we use this equation to try to make a prediction, we would realize, hey, I'm going to get a prediction, but on average it's going to be off by about that. So, and then we have, let's see, R. Okay, R is the strength of our linear relationship. All right, you find R by taking the square root of R squared, but you realize it has to have the same sign as the slope. Okay, and our slope is negative. So our slope is negative. R always has to have the same sign as the slope, so it's negative here. All right, and so what this, and it's not telling us whether data is linear. It's telling you how strong the relationship is and whether it's positive or negative. So the way you interpret R is this. You'd say, first of all, it's negative. So you'd say there's negative, and 0.96 would be a very strong relationship between the speed and the gas mileage. And remember, like anything, 0.9 or negative 0.9 is very strong. 0.8 is strong. 0.7 is marginally strong. Anything below that is weak. That's our rule of thumb. Okay, it depends on the context, but that's our rule of thumb, so to speak. And then lastly, R squared, which is that number right there. That number right there. So R squared is the percent of the change in Y that can be explained by the change in X. Or, in other words, 92.9% of the change in gas mileage is explained by the linear relationship with the speed of the car. Or is it, 90, or another way, 92.9% of the variability in gas mileage is explained by, or is correlated with, or is related to, the change in the speed of the car, the linear relationship with the speed of the car, something like that. So that is that. And so then it asks us to make a prediction. It says, in number 5, what gas mileage would be expected if the average speed is 50 miles per hour? So we just have to plug 50 in. Make sure and show it plugged in. And so that would be our prediction. And then, of course, a fair question would be, how off is this on average? I mean, you're predicting 94.93, but how off is that on that? And that's what that number is. It's how off our predictions are on average. So, and then it asks us to find a residual. You know, the residual is how far above or below the line a point is. And it is always going to be the actual y minus the predicted y. And so in this case, and so what the actual y is just that thing, the actual y value, and then the predicted y is what you get when you plug in your x into the equation. Okay, into the equation. So we get this, and what that's telling us that this point is below the line by that much. Okay, so the line over predicted. So our line is going to look something like this. It's negative. Okay, so this point right here, the point 5620, it's like right here, it is that far below the line, which doesn't seem like it's that far below the line. So it didn't over-predict so much. So the residual is that. It's the vertical distance between the point and the line. So there you go. So that's residual, and that's the main stuff in regards to linear regression that you have to know in regards to AP stats. A couple other things. All right, let's look at this question. All right. Let's look at this question here. This is the one other type of problem that can occur. Marta wishes to create the equation of the least squared regression line relating the width in centimeters and the weight in grams of her oranges. The widths of her oranges have a mean of 5.8 and a standard deviation of 1.9. The weights of our oranges have a mean of 22.7, standard deviation of 8.4. The correlation coefficient, R, is 0.89. What's the equation of the least squared regression line? Now, this is the one place on the formula sheet you need to be aware of. Whenever they give you the mean and standard deviation in regards to regression data, you know you're going to be using this little formula here. And it's at the top of your formula sheet, and it's right there. Is that the slope is equal to R over the standard deviation of Y or the standard deviation of X. And then the other thing is Y bar, the mean of the Y's and the mean of the X's. The least squared regression line always goes through that point, and so you can plug it in. And so we'll use, in essence, these two things there to find A and B. All right, and so so the first thing is to find the slope, and so I did that here. So there's our formula, and so to find the slope, it's R times the standard deviation of the Y's over the standard deviation of the X's. And so that's equal to that. Okay, so that's our slope. And then what we'll do is we'll take this equation, we'll use the fact the least squared regression line always goes through the point X bar, Y bar. All right, and we'll plug these values in. We'll plug in our Y bar, which is the mean of our Y's, plug in our X bars, which is the mean of our X's, and then plug in the slope we just found to find A. And so that is our y-intercept, and then thus we have our equation of our line. And so that's how you do that. And so then the last concept I want to talk about is what's mentioned in section 3.3 in our book, and that is if data is curved. All right, if the data has a noticeably curved pattern, what can we do? There's two situations. One that we can deal with, and that is one if data is exponential. Okay, if you look at your data and it has a noticeable curve, it's like it looks like an exponential growth thing, which the coronavirus has been doing, which I made a video on that about a month ago. Or there's an exponential decay. It's going, it's going like this. So there's some sort of exponential decay that is going on. Okay, but the important thing is you notice there's a noticeable curve. All right, it's potentially, all right, what we call exponential. All right. And it's going to be exponential if it is straightened by x in the log of y. Exponential means this is being multiplied by a common ratio as your x's go up incrementally. Okay, so and in this case it would be more than 1, and in this case r would be less than 1. But so here's the fact that you need to know. All right, and it could be asked of you. How do you straighten data that is exponential? And that is by taking the logarithm of the y values. If you do that, it will straighten the data. And by straightening the data, then we can do all this linear regression stuff that we've just talked about in this video previously. Okay, we can do all that stuff. And then we can make the equation of the least squared regression line and everything. And then the other thing, if data is showing a noticeable curve, it might be following a power law. So you notice here x is an exponent. So if x is an exponent, that's exponential. All right? But if x is a base, then it's following a power law. It's not quite as powerful as exponential, but it's like a parabola. It's like y is equal to x squared. And so what will straighten it then is you take the log of x and the log of y. And you can, by the way, you can use any base you want. You could use base e, you could use base 10. Typically we use one of those two because those are on our calculators. But and then you could do the linear regression stuff with that. But those two facts are things that have been on the AP exam, is just knowing that fact. If it follows a power law, something like y is equal to 3x squared. Okay? You notice x is a base, x and the log of y will straighten it out. And if it's following an exponential thing, like, y is equal to 2 times 3 to the x, like that, it would be x and the log of y that'll straighten that out, and you can do linear regression with it. And that's it. That's your review of Chapter 3 and of linear regression. And, of course, there's a worksheet that I want you to try to do, and I want you to send me any questions that you have. But see if you can, take this video and use it to, to do that worksheet and to think about linear regression.